And we are back. Good to see you. This is Monday, July 13th, chapter 21 here. Actually, part two, I believe. We already did part one. We did the introduction part. So the next two class periods today, we'll be doing all the reactions. Remember, I warned you there's six reactions in this chapter. So um, homework 6 will be due tonight because we'll finish 21 today after the third time on this chapter. And then quiz 5, which has reactions, I think, from 20 and 21, will be due tomorrow. So you'll be able to get with the recitation TAs or come to my office hours to get help with that. But quiz 5, it's on Learning Suite in the same spot. You should know that. Let's look at the chapter outline a little bit. Yeah, we already covered naming in the first session here. Showed you some examples, preparation, reviewed some things. We went over the general ideas of the mechanism. Yes, the carbonyl is electrophilic. It's the electrophile in this reaction. We're reacting with a number of different nucleophiles. Okay, so we've already learned a lot of nucleophiles from the hydride reductions and then the Grignard additions in chapter 20. Now we're doing some different nucleophiles, and some of these are reversible, and we'll see that. Cyanohydrin is actually reversible to form the alcohol cyanide here. We'll start with that one. I think that was one. The Vidiq reaction is number 2, imines, enamines 3 and 4, hydrations 5, and acetals, 6. So those are our main reactions. Let's start with cyanohydrin here on the board over here and see what we need to know there. Of course, we'll be going through the mechanism of all these. So use everything you know structure-wise to help you keep these reactions straight. But it's the combination of the reagents and the starting materials. We will be limited to aldehydes and ketones here. In fact, for the rest of this chapter, these 6 reactions, the carboxylic acid derivatives do have carbonyls and can undergo nucleophilic attack, but they have a leaving group on the side. There's a halide or a oxygen or nitrogen on the side of the carbonyl. So those are different type of substrates. Aldehydes and ketones do not. They have alkyl groups or hydrogen. Okay, those are not potential leaving groups off the tetrahedral intermediate. Okay, so what do we have here? The conditions and the starting material. And so the product here will be the cyanohydrin. Now we've seen that term before, hydrin. We saw the term what? Halohydrin in chapter 9 or 10 in 351. This hydrin reaction was what? With halogen and alcohol, okay? And that gave a halohydrin. The hydrin term is kind of archaic. It's persisted in the organic literature. And in this case, it gave the bromo alcohol like that. Okay, the bromo alcohol. And that would be the modern terminology, but we called this what? The bromohydrin, or halohydrin. But that was earlier. That was in addition to an alkene. Well, similar, it's a pi bond, right? Just like our pi bond here with the aldehyde. But we used that term hydrin before. I like to point out the similarities there. Okay, let's see what we're talking about here. So our reagent is sodium cyanide. In fact, we've seen cyanides before too, right? Where have we seen cyanide as a reagent? Right, for SN2 reactions. If you have primary or secondary leaving groups on alkyls, we've seen substitution, SN2 with those type of things. So add the charges here if you want to. It's a lone pair, triple bond there, and a lone pair on the nitrogen. So that's the full structure. So yeah, focus on structure. Remember, there's 3 levels of understanding in OChem. Structure, reactivity, what reagents, what starting materials give what products, and then the 3rd level is mechanism. So we will be doing the mechanism of each one of these reactions. Use the mechanism to help you keep track of the reactivity. Okay, we start though with the structure here, so we always point that out. So what can occur here? We have the partially positive carbonyl. So let's go ahead and bring our arrow down here and push the electrons up there. Okay, so that should make sense from what we've already Known there, the oxygen is more electronegative, so the 3 lone pairs there will make that with what, a negative charge. Then we have the cyanide here. We still have the hydrogen there from an aldehyde. If this is a ketone, we'd have the other alkyl group there. So what can we do at this point? Well, then we add HCl. Now, cyanide on its own is actually reversible. This can come back down and kick the cyanide back off, and it can reverse here. But if you quench the O minus here with a strong enough acid, and we'll use HCl here, then the second step is protonating that to give the product. And this can be chromatographed and purified now, this cyanohydrin here. Now this is a very useful reaction. Why? Why do we point this out as an important reaction? Well, it forms a carbon-carbon bond, okay? And plus now there are 2 functional groups here. We can convert the cyanide into a carboxylic acid or a new aldehyde at that point. We'll learn those reactions later. So this is a highly functionalized molecule. We'll see later on that we can convert this kind of thing into amino acids and other useful products here. Let's see a variation. Let's do a couple variations here. If we have acetone instead, the same set of conditions, sodium cyanide or potassium cyanide, doesn't matter. Quench with acid here. What are we going to get from acetone? Yeah, we'll get the cyanohydrin here. But notice we have the 2 methyl groups, the GEM methyl groups there. In biology, in different plants, there's this compound that's formed from cyanide. It's formed in a different way, but we'll show you synthetically how it's formed here. HCl, sodium cyanide, it forms the phenyl cyanohydrin, or benzyl cyanohydrin, I should say. And this is in pit fruits, in the pits. Maybe you've been told before, don't eat the pits of a peach or apricots. That's because this compound here can be present. Well, why not eat it? What's the issue here? Well, it is toxic. And if this does reverse, you create some cyanide, okay? And cyanide, as you know, is a toxic reagent that can react with the iron and hemoglobin and displace oxygen. In fact, it binds more tightly than oxygen does to the iron and hemoglobin, and that can lead to asphyxiation. So this is a serious issue with cyanohydrins, the reversibility of that there. Let's see, do we have a couple more examples maybe? Yeah, let's see if you can do these examples. So how about this one? Different aldehyde, sodium cyanide, HCl. What's the product there? How about this one? Like that one, you have to give the name of that aldehyde, the common name, right? There's a little review for you. Same thing there. And, oh, how about this one? Got to have a couple ketones, acetophenone, and how about cyclohexanone? Well, there's 4 for you to work on. Okay. So pause your video there if you'd like and work those 4 problems. Let's see what you got. Okay, and we're back. Let's see, we got the isopropyl there. And yeah, just add your alcohol and your cyanide there. And you don't have to show the hydrogen there. This was from an aldehyde, so that would be your cyanohydrin product. How about this one? This is cinnamaldehyde, very good. And so whatever's on the carbonyl goes along for the ride, and you get this cyanide, okay? Cyanohydrin. We could have added the cyanide here, right? Look at this. So we could have added right there. That's called the conjugate addition. And remember, what reagent does that type of addition at the beta carbon of an enone type structure? Very good, cuprates. So cuprates, remember, need the enolate resonance stabilization in order to go. But cyanides don't, okay? They're good enough charged small nucleophiles. They'll add at the carbonyl position. So you don't add there, you add there, okay? And that's how you get the cyanohydrin product. How about from acetophenone? Yeah, the phenyl group and the methyl will be there, and then the rest of the cyanohydrin. And same thing with this ketone, cyclohexanone, the alcohol, and the cyanide. Okay, so focus on the functional group and the reactivity. Remember that combination of the reagent with the carbonyl, but not with esters, not with amides, not with acid chlorides. We'll see Those type of reactions with a leaving group will give different type of products. So we're limited to aldehydes and ketones in this case. Very good. So that was reaction number 1. Let's go on to number 2 here, which are the Vidiq reactions. And pronouncing it correctly is part of the game here. It's not Vidiq, okay? It's a German guy, Georg Vidiq. In fact, he won the Nobel Prize in 1979 along with H.C. Brown, the famous American chemist at Purdue University. Brown won the Nobel Prize for hydroboration, a reaction we covered in 351. They shared the prize. Georg Vidiq from Germany, also with a very useful reaction here now. And his reagent looks like this. It has phosphorus with 3 benzenes on it, so 3 phenyls there. And then a carbon with a couple other things here. The negative charge there, and the phosphorus with 4 bonds here. Remember, phosphorus is in the same column as nitrogen, the same family. So that's how many valence electrons? 5, right? So if you have 4 bonds here, no lone pairs, phosphorus drawn like that has a plus charge, okay? Now this is called the ylide, or the Vidiq ylide. This is the actual Vidiq reagent. And ylide means a zwitterion where the 2 opposite charges are directly adjacent to each other. So we've seen a form of this term here, ylide, zwitterion. Again, a good German term there. Zwitterion means any molecule that's neutral but has 2 opposite charges within it. But an ylide, you could say, is a little bit more specialized form of a zwitterion where the 2 opposite charges are right next to each other. Now we can also draw a resonance structure of the Vidiq reagent. So double arrow, we can have the 3 benzenes and then a double bond right here on carbon, and then whatever these 2 R groups are right there. And this form is sometimes called the phosphorane. Now I'm going to give you the terms of a lot of these Vidiq intermediates and stuff. Don't worry about those. What you do need to recognize is that the ylide is the true nucleophile here in these Vidiq reagents, okay? It's going to be nucleophilic on carbon, okay? And what they're going to do here is we're going to react this reagent plus a carbonyl compound. We'll just stay with acetone right now. And what we get, the product here, is whatever this carbon is right here on the ylide gets incorporated into the product. Whatever's on that carbon, these 2 R groups in this case, get incorporated there. And here's the 2 groups that are on the aldehyde or ketone. And again, we're limited to aldehydes and ketones here, okay? Now, I'll give you a little bit of a hint here. There's a byproduct. Triphenyl phosphine oxide will be our byproduct. We won't worry about that byproduct, but that's a hint for how the mechanism is going to work, okay? So stay tuned for the mechanism. But first, let me give you a couple more examples and point out why the reaction is so useful. So a couple other examples here. Let's see, we can take ketone and use this Vidiq reagent, triphenyl phosphorane, where we just have a carbon with 2 hydrogens on it here. And that might look kind of funny, but there's a carbon here and 2 hydrogens. Sometimes we don't draw the whole thing, but that's what we mean by that reagent. Now, when you react these 2 together under inert conditions, you can't have any protic solvents or anything. Usually it's THF or methylene chloride as our solvent. The product in this case is this, okay? So again, this is just the reverse of what? Ozonolysis. Sometimes the Vidiq reaction, maybe I mentioned that last time, I think. Reverse of ozonolysis. We just take this alkene, treat it with O3. We can clip that and add in carbonyls on both sides. Get the ketone. Now this alkene here is di-substituted, okay? So this alkene's a little bit tricky to make from dehydration conditions. Why? Because a lot of times we'll get rearrangements to the more substituted alkene in this case. In fact, we showed you how to make that from a combination of what? Methyl Grignard reagent, methyl magnesium bromide, and then treatment with strong acid and heat, remember? And so the methyl group added, and then it didn't eliminate up here, it eliminated right there to give the trisubstituted alkene. But you see with the Vidiq reagent now, we can put the alkene right where we want it, and no rearrangements. It won't go over to a more substituted spot. It'll stay right where it needs to be. So we're under slightly basic conditions here. We're not under acidic conditions, so no rearrangements or no variations in the product there. Let's see. How about this variation? Let's have benzaldehyde. All aldehydes can work here. Triphenylphosphorane that has a cyclopentyl group built into it. Let's see if you can come up with that product. And how about this one? Isopropyl aldehyde here. And how about this Vidiq reagent? Okay. If you want to pause the video and try those two problems, go ahead. Let's see what you come up with. We're back. Well, the benzene will still be there. Double bond will be formed, and then whatever else is on the Vidiq gets incorporated there. Okay, so you can see it's a very useful reaction, forming carbon-carbon double bond right where you want it. Okay, that's the power of this reaction. Same thing here. We got two methyl groups here on our phosphorane. So the isopropyl, there's be our double bond, and then right there, another very useful product. Okay, so you can see what we're going to do there. All right, the hint on the mechanism was that the byproduct is triphenylphosphine oxide. Okay, so let's see if we can go through the mechanism. And you know that the phosphorane ylide is the nucleophile, right? So let's see. Let's have a simplified substrate here, just acetone, and do the mechanism. So we can draw a resonance structure of this. And we'd have the plus charge there and the negative charge right there. So that's just putting those electrons back there. Now you can do the mechanism from the neutral form here, but recognize that this is the true nucleophile with a carbanion right there on the ylide. So let's go ahead and get this guy started. Push the electrons up there. And what do we get intermediate-wise? We get O minus, tetrahedral intermediate at that point, right? And we've got phosphorus with the 3 benzenes still on it. And here's where our 2 hydrogens are from the Vidiq reagent. So we just made that bond right there. Okay? Everybody okay with that? This is sometimes called the beta-ene intermediate. Don't worry about that term. This is still a zwitterion, but it's not an ylide now. Remember, in ylide, the 2 opposite charges are right next to each other. This is 2 opposite charges. It's neutral overall, but this is zwitterion because they're not adjacent. Anyway, how do we get to triphenylphosphine oxide? This is our byproduct. So, and how do we get to the double bond? Well, we've already formed the sigma bond right here. Okay, so how do we get the pi bond there? Well, you can kind of see we've got to eliminate the oxygen and the phosphonium salt. Okay. So let's see what we can do here. Let's just put these electrons on there. And this is actually a known intermediate for this reaction, where we have a 4-membered ring. This is called an oxaphosphatane. Now, I'm not even going to draw up that term for you. You can't. The one you need to know here is phosphorane for the Vidiq reagent. And even that name, I don't know. Know how to use it, know what the structure is. I'll cut you a deal there. Don't worry so much about the nomenclature, but know the structure and the reactivity of these things. So we get here to the oxaphosphatane. Oxetane is a 4-membered ring. Oxarane is a 3-membered ether. Epoxide, we call those. But the phosphorus oxetane is the 4-membered ring with a phosphorus in it. So what can we do now? Well, let's just form the double bond right here by breaking this carbon-phosphorus bond and then put these electrons up on oxygen. That will actually get us to the phosphonium oxide salt, right? So let's see. Push these electrons down. That's going to become what? Our pi bond. Let's get that drawn. Yep, there it is right there. And look, there's our byproduct. Triphenyl phosphonium oxide, or triphenylphosphine oxide, it's sometimes called. But you can easily separate that. This is a polar compound. A lot of times the alkene is a lower boiling thing, so you can just distill that apart. But that would be our product from what? Acetone and this methylidine triphenylphosphorane to give that product right there. Very good. Let's do a couple synthesis problems now using what we know about the reaction to make different types of products. How can we make this compound using a Vidiq reaction? First of all, you should know the name of that. What is it? Styrene. Yes, John Huntsman's compound that's made in billions of dollars over the years. Styrene, okay. How can we make it? Well, it's a reverse of ozonolysis, so we can have this phosphorane plus what? Carbonyl. Yeah, we'd have to have formaldehyde, okay. That's one way to make styrene. It's actually a very expensive way. Styrene's not made using a Vidiq reaction industrially. Different types of substituted styrenes can be made this way, but this would be a way to make it. Is there another way to do the Vidiq reaction? Yes, you can reverse the carbonyl and the Vidiq reagent. So let's have benzaldehyde instead, plus what? Triphenylphosphorane methylidine, just with a carbon with two hydrogens on it. Those would be two different approaches to that same molecule, okay? So these simple synthesis problems you should be able to do. Let's do a more complicated one, maybe, with a tri-substitute alkene here. How are we going to make that? We're going to make that from what? Maybe a Vidiq reagent right here. And make sure you draw this correctly. It's phosphorus and then pH3. The 3 refers to the phenyl groups, 3 benzenes on there, and then the phosphorus, and then doubly bonded to that. So this is the phosphorane ylide right here. Could draw the resonance structure. What carbonyl compound do we need here? Oh, we need this ketone, right? We need that one, okay? So that'd be one way to do it. Is there another way? Yep. We can have this aldehyde instead. In general, aldehydes are better electrophiles, so if you have to make a choice here, these are both aldehydes here, but for this one, you see this ketone is generally lower reactivity for Vidiq, but purposes of our class, either side, you can have it. So what would we need here? We'd have to have the phosphorane right here, okay? And so that would do it to give that same type of product there. Very good. Couple other things about the Vidiq reaction. How do we form the triphenylphosphorane? So how do we make this right here? Whatever R group we have right there. How do we make that? Okay, well, it's made quite simply from the halide. So it can be a bromide or a chloride typically, and you react that first with triphenylphosphine, it's called. So that's analogous to an amine compound with phosphorus. Remember, there's 5 valence electrons, so there's a lone pair on phosphorus. When this reacts, phosphines are actually better nucleophiles than amines. So this reaction with phosphines, we don't spend a lot of time on phosphorus. We'll see phosphates a lot when we get to the biomolecules. In fact, part of the driving force for the Vidiq reaction forming the phosphine oxide is that phosphorus-oxygen bonds are very stable. And that's part of the driving force. In nature, most phosphorus is found as phosphate, which has, 4 oxygens around it. But this reaction right here works very well, and we get this product. So let's see. That's just a simple displacement. In fact, what type of reaction is that? Right, this is an SN2 reaction. We haven't covered that, but this is a good nucleophile. Even though it's neutral, and primary and secondary work best here. Tertiary is formed another way. In fact, you don't need to worry about that. For the Vidiq reaction, it has to come from a primary or a secondary leaving group. Just look at the structure. Okay, a lot comes out of the structure. This is not the Vidiq reagent, though. What do we need to get rid of here? We need to get rid of 1 hydrogen. We've got 2 there because this came from a primary halide. But what do we need to do? And we need to have an anion there, right? So yeah, we need to treat with base. And this typical base is butyllithium. Now, butyllithium looks like this, right? That's an organolithium species. How strong of a base is butyllithium? Well, it's about the strongest one we can put in bottle, okay? Yeah, we can buy commercial solutions of butyllithium. We use them all the time in the lab, but it's an extremely strong base because once it takes a proton off of something, it forms what? It forms butane. And what's the pKa of an alkane right here? The pKa is 55. So that means what? The anion from this acid is super strong. This is a super weak acid, so the converse applies. This is a super strong what? Base. And so this base, butyllithium, can take that proton, and you see that will give you the ylide. This is not the Vidiq reagent. This is the Vidiq reagent, okay? When you're making a phosphorane or a synthesis applications, you have to show the SN2 reaction from a halide and the treatment with base to form that. They're both very high yielding. A lot of times we don't even isolate the phosphonium bromide. We just treat with base. But if you leave out the base, guess what? No Vidiq reaction. Why? Because the anion's not there. The structure. You have to focus on the structure. Keep these things straight. Okay, a couple more applications. I like this one, commercial synthesis of beta carotene. I always mess up the structure, so bear with me here. Let's see if I can get this straight today. Here is our Vidiq reagent. This is done on very large scale. There's our ylide, and we react it with this dialdehyde. And let's see, can I get it right? It's making a polyene. This will be carotene. You know the reaction's working when you see your flask turn red, okay, or orange, right? Yeah, orange. Okay, carotene is the orange color. Let's see. So you have to have two equivalents of this. So it's a double Vidiq reaction, right? Here's aldehyde here. And if you have two of these Vidiq reagents, what do you get product-wise? Now here's the hard part. Sorry, I've got to look at my notes. It's a polyene with a lot of double bonds. Yeah, I'm going to run out of room. I've got to go smaller. Sorry. Oh, there we go. Okay, let's see. That's it. Highly conjugated, right? The thing will turn orange. You've got all these alkenes conjugated. Where did we form the Vidiq reaction? Oh, right there. And let's see, right here. Yeah, so you can see where the two phosphorane reagents were right there, and our dialdehyde was right in the middle. Okay. So I like to point that out to show you a commercial application. Yeah, you can get carotene from carrots. It's a little easier to make it in the lab, and there's a lot of uses of carotene as a natural dye and other things. So yeah, this is made that way. Let's see. One other one I want to point out here is stereochemistry. So here's a one that's going to give a mixture of isomers, right? So here we have an aldehyde. Here's our phosphorane. You can go through the mechanism and figure this out and verify that this is our product. But what is the product here? It gives a di-substituted alkene, right? And cis is generally the major one. That has to do with the oxyphosphatane intermediate stability. It actually prefers to have the two groups here. If you're forming a di-substituted alkene, when the phosphonium oxide eliminates, it actually prefers to have these two down. That's a nuance of the mechanism I'm not going to cover with you. You don't need to worry about that. It will often give a mixture. If you'd like to point out, though, and like to keep track of it, cis is usually major, if that is a choice there with di-substituted ones. But we'll just stick with a mix for the purposes of this class. That's probably easier. And Erin's nodding her head, too. She likes the idea. We'll just let you off the hook there, okay? But yeah, so that's a good way to do it. We know how to make trans double bonds, actually, right? from alkynes and treat with sodium metal and ammonia. Remember, we know and we know how to form these alkenes from cis-alkenes from alkynes, right? So this is really another way to form that. But here we're forming it right in the middle, the pi bond and the sigma bond together. Okay, those hydrogenation conditions just form the pi bond there. All right, very good. So let's go on to reactions 3, 4, 5, and 6. Got a few minutes here before we start out. And when we start these reactions, the next ones involving nitrogen and oxygen nucleophiles, I like to point out something a little bit more general here that has to do with equilibrium and the reversibility of things. In fact, you know, can we take a reaction that's not necessarily favored, but can we convert it into something that's going to be favored, give a productive product? So here's what we're talking about, right? Nucleophiles with carbonyls. Here's our tetrahedral intermediate. And, you know, we can protonate. So we've done that with the cyanohydrin. Gave something else with the Vidiq reaction. Well, we're going to see here coming up that we can actually lose water here. And we can form a double bond to our nucleophile in the case of the imines. Or, you know, we can add another nucleophile here in the case of the acetals. So here's our products here, ultimately. The mechanisms, yeah, will be a little bit complicated here. But just in general, for any reaction, we can draw an equilibrium expression, right? So K here equals what? K equals the product, the concentration of that product, and it might be different things for different reactions, okay? But the principle holds here, okay? In the numerator is where the concentration of the product's going to be. And then water, you know, is also a product if it eliminates here in the case of the enamines and imines, actually. And we'll see loss of water when we form the acetals here. So ultimately, water is a product in the rest of these reactions. And this would be over what? The concentration of the starting material and the concentration of the nucleophile. Okay, so let's say here we have a case where K is actually smaller than 1. Now, the magnitude of K has meaning, right? If K is a very large number, that means what? The product is highly favored, right? Keep your numerator and your denominator straight here. There is a little bit of math in OChem, not very much, but conceptually we need to use a little math sometime. But I'm pointing out here, if K is really small, and K can be super small actually, and we can still get a good yield of product. How can that be? Well, we need to apply what? Le Chatelier's principle, the French guy, right? Le Chatelier. And what does chat mean in French? Cat. Catalysis, maybe. Oh, it ties in with what we're talking about in chemistry. No, there's no connection between Le Chatelier and catalysis. But he had the idea straight. He said a system at equilibrium, if a shock is applied, the concentrations will adjust to respond to that shock applied to the equilibrium. So let's apply a shock here. Let's say we're getting a real low concentration of product. What can we do here? Well, we can remove the water. Remove the water. Lower the concentration of water. Distill off the water. And what will that do? In order to maintain the numerical value K for the system, what will occur here? Yeah, the concentration of this other factor in the numerator will have to go up, corresponding to the lowering of the concentration of water. So if we remove water from the equilibrium, we'll drive the reaction forward, even if K is not favored. Okay, so you got the idea here. You've seen this in other systems. Here, a nucleophile is in the denominator. So what do we want to do there? If we increase the concentration of the nucleophile, look, we'll have to increase then the concentration of the product in order to maintain K. It's the same, okay, even though it's small. Same thing here. We can increase the amount of the starting material. Well, that kind of lowers our yield overall, so that's really not the best way to go. What's typically done is remove the byproduct, water, or use more nucleophile, okay? And that lets you keep that in mind. So, yeah, so let's go into reaction 3 here. Let's see what we need to know here. This will be imine formation. And imine formation will involve a aldehyde or ketone with a primary amine. And the amine has to be primary, okay? So primary meaning just one alkyl group on the amine, so it's a nitrogen with two hydrogens on it. These two hydrogens will be important for the mechanism here. And what do we get for the product? We're going to get the imine, okay? So this is from an aldehyde, so we have hydrogen and just a methyl group there. And our imine is what? A CN double bond, okay? And you can see, where did the two hydrogens go and where did the oxygen go? Well, water, okay? So typically water is removed. It's either heated up and distilled off, or you can dehydrate the whole system with molecular sieves, which is a very hydrophilic solid material, which will actually occlude or grab onto the water and help drive the equilibrium toward the imine formation. Let's look at some other examples of this, and then we'll turn you loose to figure out the mechanism. How about this one here? Another aldehyde, benzaldehyde, plus ethylamine. What will that form? Yep. So we'd have the double bond here and then the ethyl group right there. Okay. How about a ketone? Cyclohexanone. And oh, how about benzylamine? Now you should remember what benzyl means. That means a benzene and a methylene. I'll draw out the structure. So we'll have the imine right there and then the benzyl group on the imine. So these are, again, primary amines. Have to be limited to primary amines. How about this one here? Another ketone plus, how about isopropyl amine? Okay. So there's where acetone was, and then there's the isopropyl amine. Okay, let's give you a hint on the mechanism before we get into that. Let's look at the rate profile of the reaction. Okay. What do we mean by the rate? How fast the reaction can occur, okay? And let's look at the speed or the rate right here. So that's how fast the reaction is getting. And let's look at the pH. In fact, it's known that if you add a little bit of weak acid, this is going to make the reaction the fastest. Let's look at 7, 0, up to 14 here. And here's how the rate profile looks. Starts out at 0, goes up, peaks at about 5, and then tapers off to nothing at 14. This is the optimal rate. The fastest rate here is at about pH 5, which means what? We know something that has a pKa around 5. What is it? Yeah, carboxylic acid. So a lot of times we just add a little bit of acetic acid in order to get these reactions to go fast. What does this mean here? If you have a pH of 0 here for an imine formation reaction, you don't get any product. It's just too darn slow. And why is that? The concentration of hydronium ion is super high, okay? You need to think about the structure and how that's going to affect the mechanism. What if we're way out here at 14? That means hydroxide's super high, and that'll give a different type of reaction with aldehydes and ketones, an aldol reaction. We'll learn about that later, okay? So that'll give something else. The sweet spot, we say, for imine and enamine, this applies for the enamine also, is right here at pH 5. So let's see. Let's turn you loose here on an activity sheet. Let's go back up here and see what we need to say about that. Oh, there it is. These activity sheets are also on Learning Suite under Content. I point them out from time to time in class. If we were in class for real, I'd have you in small groups right now. And you can do that if you're watching these videos and know someone in the class. Get with them and work through this. But here's the challenge, right? Imine formation, whilst primary amine, aldehyde ketone, provide electron pushing mechanism. Start with a protonation of the carbonyl oxygen using acid catalysis. Okay, so if acetic acid is in there, it will go at pH 7 if you don't add acid, but it'll be a lot slower than if you have it at pH 5. Justify the formation of the carbon-nitrogen double bond in this case. So yeah, have at it. And we are back. Let's look at the mechanism here. If we can come back to the board here. Let's go through the mechanism of imine formation and hopefully see what we've got. Start with the protonation of the carbonyl. So if we've got acid, acetic acid, or if you just want to say proton, that's fine. But protonate that guy, and let's see what we got. We'll get this. Now, why is a little bit of acid going to help us? Well, if we protonate this, what does that do to the electrophilicity, okay, and the attack of the nucleophile? This is increasing, this positive charge on the carbon. It's not just here. We could draw a resonance structure with more plus charge there, right? So this protonated carbonyl is important. We'll see that over and over again in coming chapters as well, okay? So what have we got here? We've got our nucleophile, which is ethylamine. There it is. Let's go ahead and attack. So we'll get this, OH, hydrogen, 2 on there. And look, we still got a plus charge. Why do I have a plus charge on that nitrogen right now? Right, 2 hydrogens and the ethyl group. This will have a plus charge. We just used the lone pair to attack the carbonyl, push the electrons off. This is an alcohol now, okay? This is sometimes called an aldolamine, okay, or a hydroxyamine. They're not stable. We're going to lose water here in a second. How do we justify forming the imine? Well, let's see. We can transfer that proton from the ammonium cation to the alcohol, okay? Why are we doing that? Well, we're going to convert that alcohol into a better leaving group, okay? We've talked about leaving groups before, including alcohols. Alcohols, OH groups on their own are terrible leaving groups. Only under strong basic conditions can you consider hydroxyl as a leaving group. But a hydronium ion, that can be a leaving group, right? Because we got to get rid of water. Well, there it is right there. Let's pull those electrons out, put that second lone pair. It's OH2O already, right? And this charge will go away if we put that lone pair back on there. Okay, we're not quite to the imine yet, but what do we get? We get carbocation right there. Okay, and water. Okay, so at least we've accounted for the byproduct. And then what? We've got a pair of electrons that can come down here now and give us the carbon-nitrogen double bond. That's the key step, I'd say. We still have the ethyl group on there. Is that correct, what I've got drawn there? No. What do I need to add here? Yeah, a plus charge on nitrogen. Okay. That's called an aminium cation, and we'll see aminium cations as other intermediates. In fact, these are really common in biochemical transformations to make different cofactors and different metabolisms of amino acids. These aminium cations are there. But we're under neutral conditions or weakly acidic conditions, so what can we do? We can take off that OH group. We've got acetate in here. We've got water. So we've got a couple of weak bases, and that will give us the final product, okay? The imine product, okay? So, yeah. Look at the steps there. Make sure you can follow through there. There are different ways for us to ask about that on a quiz or a test. In fact, the quizzes, I think we got a couple quizzes where you'll have a mechanism you'll have to do on this quiz 5, actually. You'll have to go through some of these, okay? Yeah, so that would be our mechanism there for that. It is reversible. If we take this and treat it with strong acid and water, we can go back actually through all these same intermediates and go back to this product. And why does it reverse? Well, now water is present. At first, when we formed the imine, we didn't have any water present. We were taking water off. You can use water as a solvent here, you see, with a high concentration and acid catalysis and go backwards completely here. And what that will do is you'll protonate back to the aminium ion, attack with water, okay, and just lose the proton off there, create this into a better leaving group, the ammonium group can come back off as the lone pair comes back down. So you already see all the intermediates for the reversibility step. I'm not going to give you this mechanism for the reverse, but you should know how to form the reaction in the forward direction and the reverse direction. That's a good exercise to go through there. But again, primary amine, that's the key thing here, and then aldehyde or ketone for either of those products. Okay, yeah, and we already gave you some examples there. So let's see. We're close to the end here, I think. So maybe we'll stop here for the first hour. Yep. And yeah, stay tuned here for reactions 4, 5, and 6 coming up. We'll see you next hour.